So during the break, I was looking at this Wikipedia page on activation functions. So maybe I'll post it in the chat so the others can see as well later on. And there's really a lot of choices available when it comes to creating model architectures and what kind of neural networks to use. There's just one example of different kinds of nonlinear activation functions people use different purposes, of course. So there's, for example, an identity function, which is nothing but just a straight line. So it doesn't do anything. There's, for example, a step function. There's these logistic or sigmoid functions that look like this. There's the hyperbolic tangent that we used. There's this ReLU that we used, which is 0 and then positive values. There's a whole bunch of different activation functions. They all give you different types of sort of prediction behaviors. And these are all part of hyperparameter optimization when it comes to tuning these neural networks. Okay. So that was just a brief sort of overview of what neural networks are. We trained it on some dummy data that I generated. I didn't tell you what is the true relation between the X and the Ys that were given for the data. But in real life, you will never know what these data will be. But I can tell you that now, like as part of the workshop or in a instruction setting, I can tell you that, for example, the first column I think was a sine, the second column was an exponential as a function of X, and the third column was, I think, a quadratic function of X, and fourth column was, I think, cubic function of X or something like that. Okay, and so you were really learning these functions without knowing what the true function is. You were just learning it from the data. Okay. So now let's try to contextualize it to a more materials design problem. And if you can all open the session 3 notebook, that's the one we'll be working on for this session. Okay. So yeah, sorry, 1 second. Yeah. All right, so here we'll do a simple case study on inverse design, okay? So when it comes to designing materials, there's a whole lot of different types of materials, okay? So for example, Vibhor was saying that he works in the microstructures group, but you know, we all have our different material systems that we might be working on. So for example, maybe metals, maybe stochastic foams, architected lattices. It's really 3D printed structures. There's a whole range of variety, okay? And the way we characterize or model these materials is by doing trial and error, okay? So maybe, you know, you take your material, you go to the mechanical testing lab, you put it under some kind of deformation, you get the anisotropy, you get the stress strain relations, maybe curvature distributions, basically characterize your material. But you can have, you know, 4, 5, 10, 100, 200 parameters, and you soon realize that it becomes computationally and experimentally very, very expensive if you do it with a trial and error approach. So let's say you want to optimize your microstructure, or let's say your metal specimen or your foam design, and you have 10 design parameters, you want to optimize it for maximum toughness, let's say. And if you're a simulations person, then you will maybe run 100,000 different simulations to find the best combination of parameters that will give you maximum toughness. But it's even more hopeless if you are an experimentalist, because you can't even do 100,000 simulations. At best, you can do maybe 10, 20 or so simulations. And this is just for one design objective. You might want to do it for 100 different design objectives. You have to repeat the process all over again. So this is where machine learning and data-driven methods come in. And because these, in this case, neural networks, but any other machine learning method out there, there's a whole bunch of them, they can learn really nonlinear, high-dimensional maps between the design space, okay, and the property space. Because you can learn these high-dimensional sort of maps between these two spaces, you can then start to sort of quickly find optimal designs, optimal parameters that help you achieve, let's say, targeted properties or exotic properties, if that's what you're looking for, okay? And so that's the role of machine learning in materials design. So for this case study, we're going to be studying a class of materials that we recently looked at. And these are called sphenoidal metamaterials. And I'm not going to go into the details of these metamaterials and what they are and so on, because that sort of deviates from the point of this course, which is to get an idea of how to use machine learning in these contexts and not really do a particular materials design. So just as a very high-level introduction, what is the problem at hand? We have a design space, okay, which has 4 design parameters, okay? And as a machine learning, applied machine learning person, you don't, you don't have to know all the details, at least for this context. You don't have to know all the details of what these design parameters and so on are. But let's just say you have 4 design parameters that you're concerned with. And by changing these design parameters, you can get really different kinds of structures that have very different kinds of properties. And so the properties that we'll look at is stiffness. Okay, so if you go back to your basic material science or mechanics courses that you might have studied in undergraduate, stiffness is given by, let's say, a stiffness matrix, which might have, depending on the different symmetries and so on, has, let's say 9 constants, okay? So in this case, for these particular materials, your stiffness is given by 9 constants, 9, let's say, stiffness parameters. And you can visualize these stiffness, these anisotropic stiffnesses in these 3D plots, okay? So for example, if you pick any point on this surface here, that tells you the Young's modulus in that direction. So if you look at the left-hand plot, it tells you that this structure has a very high stiffness in the horizontal plane, but very low stiffness in the vertical plane. This one here has a very high stiffness in the vertical plane, very low stiffness in the horizontal. And this one, for example, has high stiffness along XYZ, but very low stiffness otherwise. But really, let's not get deviated by the problem, which is machine learning here rather than the materials problem. If you're not interested, then all you need to know is that you have 4 design parameters and 9 stiffness constants, which can be visualized in this fashion. Okay. So X, if you relate it back to your previous session, X is 4 design variables, 4 dimensions, Y is 9 dimensions. Okay. So now let's say you are trying to find a set of parameters that give you a certain target property, okay? So instead of going from design space to property and doing a trial and error approach, we want to do the opposite. We want to be able to reverse engineer a design given a target property. So let's say I have given you a stress strain map, or maybe I gave you the 9 stiffness constants that I want for this material. Find me the material that will give me that property. So that's inverse design, okay? So I want to be able to have a machine learning model where stiffness comes in and I get the design that has that stiffness, all right? So what I'll do is I'll go ahead, I'll generate a big data set. And this data set will contain a lot of these materials, like different designs, which will give me these materials. and then I will have a lot of their stiffnesses. And then with that data set, I can try to create a machine learning model that instead of taking the design, actually takes in the stiffness. So the stiffness A comes into this inverse design neural network, predicts a certain topology or certain design B, and that should have the same property as, should have the same stiffness as what was your query. Is the premise of the problem clear? Any questions? No? If you're not familiar with materials, and if you're not familiar with what stiffness is and so on, just think of stiffness is something that we want to achieve. This is your query, your target stiffness. I want to find the design. All right. All right. So then let's say I create this neural network. This neural network takes in some stiffness A, which is my target. It predicts some design or topology B. And then I compare it to topology A. The thing is, I cannot do that. Why? The reason why I cannot do that is because multiple designs, multiple materials can have the same stiffness. So as a very crude example, if I say, give me a metal or a metal alloy, which has a Young's modulus of 200 megapascals. But there's hundreds of metal alloy compositions that can give you 200 megapascals, right? So there's no one single correct answer. There's actually multiple correct answers. So for stiffness A, I can have different topologies, which are all correct answers. So this problem is ill-posed, okay? Which means I cannot compare this topology A and this topology B because they're both correct answers, but on paper, they are very different from each other. Is that idea clear? Both A and B have the same stiffness, but A and B are very, like the design itself is very different from each other. Okay, any questions before I move forward? No? Okay. So how can we fix this problem? So let's go back to the network again. In comes a stiffness A, okay? Passes through an inverse design neural network, let's say, and gives you some design B or topology B. I can do finite element analysis or just any other simulation method, okay, and compute a stiffness B. All right. Now, I don't really care if design A and design B are the same or not. I really don't care. As long as design B, which has stiffness B, so stiffness A and stiffness B are the same, I really don't care if the designs are different or not, or the same or not. Stiffness A and stiffness B must be the same, irrespective of topology A and topology B being same or not. Because that's what the problem statement is. I have a target stiffness. I should be able to achieve that stiffness. Just find me this design. So I take this prediction from the inverse network. I do a simulation on it, and I get a certain stiffness B. Okay. And I can then compare stiffness A and stiffness B, maybe define an error metric, error between these two stiffnesses, and train my neural network. Now, the problem is, as you saw, while training, we do maybe 1,000 iterations, maybe on 10,000 data points in our training data set. So 100 to 10,000 data points multiplied by 1,000 iterations. How much is that? 10 million? So you'll have to do your simulations 10 million times during training to be able to train your neural network. And that is incredibly expensive. Each of these simulations can take maybe 5 minutes. For this particular example, for a more difficult problem, it might take you an hour to do a simulation. So it's not really possible to do the simulation on the fly while you're training your inverse neural network, inverse design neural network, okay? So how do we fix that problem? So what we do is we can replace this simulation part, this FEM homogenization or simulation part, with another neural network, okay? Let's call this neural network the forward neural network. Why is it forward? Because it's how we usually characterize materials, right? So you have a material here or a design or whatever, you characterize it to get its property. So hence it's called a forward neural network. So given a big data set, I can first train a neural network that learns the map from the design to the stiffness property, similar to what we did before, similar to the previous session where you had some X's and you had some Y's. I can learn this relation beforehand. So that's why I'm saying it's pre-training, okay? And then once you've trained it and you have sufficiently good accuracy in predicting the stiffness, I can remove this simulation component here, replace it with a neural network. Which means now I have two neural networks. I have an inverse design neural network. I have a forward neural network. Okay, the forward neural network goes from design to stiffness. The inverse neural network goes from stiffness to design. Okay, I train the forward one first, I'll train the inverse one second, and you'll see that with this kind of setup, you can actually have an inverse design network, which given a property will give you the reverse engineer the right design for you. So before I go into implementations, I'd like to take a minute and see if you have questions or if you understood what the approach will be on a high level. Anyone? Questions? No?
Hey Sid, can I ask a question?
Yeah.
I don't fully understand the problem yet, and I don't fully understand the terminology yet, but I think getting my hands dirty will help. Just trying to understand the forward neural network. Is that the same thing then as a quote unquote traditional neural network?
Yes. So your forward neural network is just sort of a surrogate of your design to property. Okay. So that you don't have to do simulations all the time.
Yeah.
Each of these simulations, so if I go here, each of these simulations will take you 5 minutes. You have 10,000 data points. You have to do this 1,000 iterations for training your inverse network. So that means 1,000 times 10,000, you have to do 10 million simulations to train this inverse neural network. And if each simulation takes 5 minutes, you're talking 5 million minutes of computing, which is not possible. But what I want is a cheap approximation of the simulation. Okay?
Yeah, that makes sense. So first we try and create a neural network then to translate a topology into a stiffness.
Yes.
And then we try and go the other way around, basically. So we were looking for a certain stiffness. What kind of topology would fit with this?
Exactly. Yeah.
Okay. Thanks.
The idea of the forward is just so that we can have a cheap approximation of the expensive simulations.
Yeah, makes sense. Thank you.
And once you found your magic topology, you can always do a high fidelity, high resolution simulation and get the exact stiffness of that, or like get a good characterization, or maybe even go 3D print it and give it a try. Okay. All right, so let's try to implement this, but does anyone else have any questions? Nitin, you were saying I should emphasize more on the forward part.
Yeah, I understand what you like. Remaining like removing the FEM homogenization things.
Right.
I want that.
Okay, sounds good. So let's get our hands dirty a little bit. Okay, so I'm just going to simply load the data here. It's just simple NumPy loading some CSV files and then converting it to Torch tensors, okay? Whenever you load a data, it's always a good idea to, check how your data looks like. So I can always say, for example, print X, okay? See, X looks like this. It's a lot of data rows, like a lot of data points, and you have 4 columns. So remember I was telling you, you have 4 design parameters and 9 stiffness constants, okay? So this is print X, you have a lot of data points, you have 4 design parameters or 4 dimensions of X if you don't want to think about the materials aspect. Okay, so you have this, and I can also print maybe X dot shape. So if I print X dot shape, it tells me there's 21,300 data points, and I have 4 dimensions or 4 design parameters for each of those data points. Okay, so I can define XDim as 4. So that's the dimensions of X. All right. Let's now do the same thing with Y. So Y is my stiffness, print Y. You see a lot of data points again. It's maybe better to just simply do Y dot shape. Now again, see 21,300 data points and 9 columns being the 9 stiffness constants I was telling you about. So then I can simply say Y dim equals 9. All right. Straightforward. Okay, so you have X, which is 4 dimensions, Y, which is 9 dimensions. Let's first do the forward neural network. So this cheap approximation that we were talking about from topology to stiffness, okay? So remember, topology is given by 4 parameters, stiffness is given by 9. So let's create a neural network. So we have 2 neural networks now. So I'll just use, instead of calling it NN, I'll just call it forward NN. Okay, so forward NN is torch.nn.sequential. All right. And then say torch.nn.linear. Any idea what should be the argument here? Can anyone help me with it? What should I write?
4,16.
That's correct. Well, you have the answer. Oh.
Yeah. I didn't look at the answer though.
All right. Okay. Oh, maybe I should delete the. Let me clear the outputs so you don't see the answers. All right. So you have restart. Let me quickly import again. All right, so I can just, instead of 4, maybe I'll just say xdim, because xdim we just defined it to be as 4. Xdim 16. All right, and then we'll say torch.nn.relu. Okay. Then what should come next? Can anyone help me? We have 4 hidden layers, each of size 16.
So 16, 16.
That's correct. Yes. 16, 16, and then I can have torch.nn.relu. Okay, and we do it, let's say 3 more times. Okay, and then here you'll be torch.nn.linear and 16, comma, this time we will have ydim because that's the output dimension that you want, which in this case would be 9. Okay. So we're done with this, and that's what we see. So we go from 4 to 16, 16 to 16, 16, 16, 16, 16, 16, 9. And we have ReLUs in the middle. Okay. So now we have our neural network. Let's try to train it. So we say a learning rate of, let's say, 0.01. Let's create maybe a loss history. Okay. we need to define an optimizer. So we say optimizer equals torch.optim.Adam. And here we will pass the parameters of the neural network for the forward problem. Okay. So we say forward NN dot parameters this, and then we define the learning rate as well. So LR. Okay. That's your optimizer. We remove any previous existing gradients. So we say 0 grad. And all very similar to what we did before. Now let's make a prediction. So we say y pred is forward NN on X. Okay. Now let's compute the loss or the error between these predictions. So we will say, what was the true data that we have? Sorry. So the true data is X and Y, which means we will say loss torch.mean y pred minus y, we square it, and then we take a mean. We also talked about in one of the exercises, if you want to do maybe an absolute error, so you can also do torch.absolute, and that's how it will be if you want to do mean of absolute error. Okay, well, let's use the mean of squared error for now. Then we append it to our loss history just for post-processing. Loss.detach.item. And we do the backwards, so we can compute the gradients of gradient of the loss with respect to the forward neural network parameters. So we say loss.backward. And again, instead of updating the parameters ourselves, we let the optimizer do it for us. So we say optimizer.step. Right. Let's run this code. Should be fairly fast. Maybe 3 to 4 seconds. We're done, and we can now look at the loss history. And we see it very nicely starts to go down at about 1,000 iterations. It's kind of saturated. And we can sort of start to think our neural network is trained. Okay, very similar to previous session. Any questions? No? All right, so that was our forward model, where we go from topology to stiffness as a cheap approximation. Now let's try to go from stiffness to topology. And keep in mind, the idea is you have your input stiffness, you get a topology, you reconstruct the stiffness of that topology, and then compare this reconstructed stiffness to the input stiffness. Okay? And it will be a little bit different than what we've been doing so far. Okay, so let's create an inverse neural network. So let's call it inv.nn, which is different from forward NN. So you have torch.nn.sequential, torch.nn.linear. But this time we will go from stiffness to topology. So can anyone help me? What should I write here?
Y dimensions and 20.
Right? Does everyone agree? Right, so we have this, then we go torch.nn.relu. Okay. And then we can copy paste to save some time from 20, 20, 20 relu, and then here instead of ydim, we will have xdim, because now we're trying to predict a topology which is given by 4 design parameters. Okay. Let's see how our inverse design neural network looks like. Again, 9 to 20 and 20, 20, 20, so on. And we end at 4. Okay. Now let's try to train this neural network. So again, we have LR equals 0.01. You've seen it a billion times by now, I suppose. So you have loss history. Let's remove any, oh, before we do that, we need to define the optimizer. So we will say optimizer equals torch.optim.atom LR equals LR. Here's the difference. Last time, when we created our optimizer, we passed it the parameters of the forward neural network. This time, we want to optimize the inverse network, not the forward one. Therefore, we will pass the parameters of the inverse neural network here. Okay. So now the optimizer will only act on the inverse, not on the forward. Let's remove any previous gradient. So 0 grad, pretty standard by now. And this is here, where the main difference comes. So you have to make an inverse prediction, which is given a desired stiffness, we predict a design. Okay. So let's say you say X pred equals NN Y. Okay. Look how it's different from the previous case. Here we say Y pred is forward NN of X. But instead here we're saying X pred is inverse NN of Y. Okay. Now, if I were to say a loss will be X, whatever, torch dot mean X pred minus X. Okay. If I were to try to do this, this wouldn't work, which is the ill-posedness we were talking about. So let's try not to do that. But rather what we'll do is reconstruct the stiffness of the predicted design with the forward NN. So we take our X pred and we reconstruct the stiffness. So we say Y rec is forward NN X pred like this. Does everyone agree what's going on here? You started from a stiffness Y, predicted a design X, and then you reconstruct the stiffness of the design X using the forward NN, which is this Y rec, instead of computing a loss on the X. Any questions? Yeah. So you have your Y rec. Let's now compute our loss. So we'll say loss equals torch dot mean. Okay. There will be the square, but what we'll write here is going to be important. Here we will write Y rec minus Y. Okay. So instead of computing the loss on X, because we know that doesn't work, it's ill-posed, there's several different correct X's. We actually compute the difference between the reconstructed stiffness and the stiffness that we want. Okay. But one thing you have to keep in mind, even though the loss is in terms of Y, what is optimized is actually the inverse neural network. Why? Because that's part of your optimizer here. Okay. Even though the inverse NN predicts X, this X, because of the computational graph, goes through the forward NN and is now linked to Y. So this inverse NN is part of the computational graph needed to achieve Y rec. And now the loss is computed in terms of Y rec. Okay, so then they store loss history dot append loss dot attach dot item loss dot backward because we want to compute the derivatives And again, we say optimizer.step. But again, need to keep in mind that the optimizer is acting on inverse NN, not the forward NN, not nothing else, even though the loss is computed in terms of Y and not X. And let's train it. And let's look at how the loss history looks like. We see the loss history goes down quite well, almost reaching 10 to the power minus 4 after about 600 iterations. So before I look at the accuracy and everything, let's just take a few minutes. Does anyone have a question? Let's have a discussion about what happened.
Yeah, Sid, I have a question.
Yeah.
So if I go back to the diagram which you showed in one of your slides, so we start with stiffness A, train the inverse design neural network, and we can get multiple topologies B, right? And for those topologies, then we run the forward design neural network, and we get stiffnesses, and then if we see if those new stiffnesses match with the original one, that is our design. So it's intuitively difficult for me to understand because the data we are using for the inverse neural network and the forward neural network is the same.
Yeah.
So all the possible topologies B, when we run the forward neural network, we should get the same stiffness for all of those topologies, right?
Yes.
So it might be the case that, okay, we are getting different values of stiffness for all those possible topologies, but yeah, intuitively, how to understand this? I hope you got my question.
Yeah. So you work in metals. I'll try to give you an example of metals. Okay.
Yeah.
You work in metals, right? If I understand.
Yes.
Yeah. All right. So let's say I want you to propose me a metal which has a Young's modulus of 200 megapascals. Okay.
Yeah.
And let's ignore the reality. Let's just say titanium also has 200 megapascals, which is the same as steel. Okay, for now. All right. So stiffness A is, let's say, 200 megapascals. Okay. This in your data set, you will have both steel and titanium, which both have 200 megapascals.
Yeah.
In your data set. But let's say during training, 200 megapascals comes in here. Okay. The inverse network doesn't know which 200 megapascal this is coming from. Is it coming from titanium? It is coming from steel? It doesn't know. It just randomly makes a prediction. Let's say it proposes titanium. Okay.
Yeah.
Proposes titanium. You go to the forward neural network. Forward neural network says, well, titanium has 200. Forward doesn't care. Forward always gives you the right answer, which is titanium has 200. Steel also has 200. So let's say inverse predicts copper. Forward model will tell you, well, copper has a Young's modulus of only 50, which means which will indicate inverse, well, whatever I just predicted, which was copper, is a bad prediction. Let's try predicting something else. Then it predicts steel. Well, steel forward tells you you did a good prediction. It has 200, which was your required target. So you reached at a good decision. Maybe next time the inverse does predict titanium as well. And forward tells, well, this time also you're right. Okay. So then it will, it will predict both steel and titanium.
Yeah.
We're not doing very advanced machine learning where we can actually make the inverse network predict both titanium and steel sort of like at the same time. But here in this simple case, we'll just make it predict one. So for given 200 megapascals, maybe it predicts titanium, but there are other possibilities we're not that advanced enough to find all the possibilities. We were okay with finding just one possibility. Does that answer your question?
Yeah, I understand.
Okay.
Thanks.
Again, if it predicts copper, then the forward will say, well, you predict something that has a very low Young's modulus, you're completely incorrect. Make another guess.
Yeah.
Yeah. Any other questions? No? Okay. I think we'll have plenty of time to sort of play around with these during the exercise session. Anyways. Okay. So you now have your inverse neural network trained, you have your forward neural network trained. Let's try to evaluate the accuracies. So again, it's just some function to check accuracies. And now I'm loading the test data. Okay, so this test data is different from the training data, and both neural networks have not seen this test data before. So I'll load my X and Y. Okay, and so for given target stiffness Y, the job is to now predict a certain design or certain topology. Okay, so what I'll do is this. I'll say X spread is inverse NN Y. Okay, so there's a target stiffness Y, I'm predicting X spread. Okay, and I can also, for example, print Y. Y is all of your different target stiffnesses. I can print X spread. For each of those target stiffnesses, I'm getting all of these different designs. As a matter of fact, you can see what is the grad function here. The grad function is basically addition and matrix multiplications and so on, which is basically representing the computational graph of this inverse neural network. All right. So you have some X spread now for some given target Y. Let's plot the accuracy between the design parameters for a second. Okay, so let's say the true design parameters were X and the predicting design parameters are X spread. And you see, except the first dimension of your design parameter, the remaining three are super bad. R squared about 0.14, completely far away from the line. For a second, you might think we did something wrong. But that's exactly what is expected. That is exactly what was the problem of why we needed two neural networks in the first place. This tells me that what doesn't matter what the true design parameter was, the final design that this neural network is predicting is completely different from what the true design is, and that's okay. Because as long as they have both the same stiffness, I'm okay with the proposed design, right? And that can actually be verified here. So you take all your predicted designs, okay? And you can reconstruct the stiffness using this forward neural network. So let's say Y-rec is forward neural network X spread. Okay, let's apply this. And now let's do the same plot, but this time for the true target stiffness, which in this case is Y, versus the reconstructed target stiffness, which is the stiffness of the proposed designs. So you say Y-rec, and if you plot it, voila. You see very good reconstruction accuracies, which means that even though the predicted designs do not match the true design from the data set, it doesn't matter, I don't care. The reconstructed stiffness of the proposed design is exactly what I wanted as the target. That's pretty much it. So, what do you all have to say? Any questions, anything?
It makes a lot of sense. It is all I have to say right now. I'm not too big, I must say, on the material science part, but your explanations, they make a lot of sense. So
Okay,
thanks.
thanks. Okay. Anyone else? Vibhor, does that answer your question from before?
Yeah, that answers. But I have one more question. Since you said that in the end, we don't really care how the topology is, as long as we are getting the stiffness what we want. Have you ever come across a situation where the topology predicted is not physically possible?
Yes, that's a very valid point. And I wish if that was not the case, then Prakash would be really happy for his PhD.
Okay.
But unfortunately, that is indeed one of the problems, which is that the inverse neural network can always, so in some ways, the inverse neural network is trying to beat the forward neural network. And, you know, instead of proposing legit designs, it can try to cheat its way out by predicting nonsensical values that might still give valid reconstruction property.
Yeah.
Okay. Therefore, this problem is simple, and that's why I chose it for this workshop. But in real cases, you know, people apply these to all kinds of things, not just materials, even for like drug design, molecule design for you know, medicines, chemistry, designing alloys, and so on, where, you know, the predictions from the inverse don't necessarily have to make sense. You can predict nonsensical designs, and still cheat your way through the forward neural network, basically.
Yeah. So it's application specific.
Of course. So yeah, with any machine learning, you have to pay attention to the application at hand, and it does require a lot of domain knowledge. Saying that, you know, you just take machine learning as a black box, apply it to any problem, and it's done within a day or so. It's never happens.
Yeah. Okay. Thanks.
Okay. Any other questions?
Yes, I also got a question. If I am not mistaken, we can use this configuration because the output of the forward network is a unique value, right?
Yes.
But
so every design has a unique value.
Exactly. But how would be the case if the stiffness were something different, like you have many possibilities or something like that?
So yeah, again, then it would be incredibly challenging as well, because your inverse problem was ill posed, but you made it well posed by you know, sort of adding this forward problem on top of it, which is well posed. But if you stack another ill posed problem on another ill posed problem, you sort of overcomplicate, even further complicate the ill-posedness, and it becomes even more challenging. So at some point you would need to, you know, include a module or include, I mean, it's very problem specific, but at some point in your architecture, you would need to have something that can tell you, hey, whatever you're predicting is right. Okay. Anyone else? We can further discuss this during the exercise sessions. They're not very intense for this session. I chose it intentionally so you can read the code over again, try to play with it, try to really go to town with it, just go crazy with the code. Try different data points, different amounts of data, different optimizers, play with the learning rates, play with the optimizer, try different optimizers, it's all in the exercise. Try different loss functions, okay? I would definitely recommend, I didn't add it in the notebook, but I would definitely recommend trying to train the neural network using this loss, which is training directly on the loss of the designs. And maybe Prakash and Kuber, you can sort of help them out with it. It's not in the notebook, but I would definitely recommend trying this out. Okay. Yeah, so maybe let's go to the breakout rooms. Right, welcome back, everyone. I hope everyone was able to make their way through the exercises. Yeah, so to wrap things up, that was a very high level introduction to machine learning for materials design, but also not really limited to materials design. Feel free to use these neural networks for all kinds of applications that might arise. And to summarize, we started with just creating very basic tensors, manipulating them, tracking their gradients, using them for automatic differentiation so we can compute gradients. Then we moved on to doing some very simple optimization problems like curve fitting and so on. We then finally created a simple neural network, and then we deployed those neural networks in this sort of 2 neural network setup to inverse design certain materials with target properties. Yeah, and that's pretty much it. And even though it was a very brief introduction, I would very much encourage you to explore this area. There's a lot more complex neural networks to explore, more complex problems to solve. And I hope you have an exciting time learning more about this area. Okay, and any questions at this point before we wrap up? No?
Can I ask a quick question if no one else has one? So this was a good start, and I'm curious, what would be your recommendation for the next thing to look into? So what's the biggest improvements that we can make from here on out?
Yeah, so this was just, as I mentioned, very basic. The next thing would be to start looking at things in a more formal setting. So like, what are the ways of treating the data? What kind of pre-processing you need to do on the data? What are some of the thumb rules and heuristics in designing good model architectures for different kinds of data? Do you need to maybe do some cleanup? Do you need to do some denoising? One needs to realize that data is way more important than modeling. Okay, so like understanding the data, getting an intuitive understanding of what's going wrong, where it's going wrong, why is the neural network predicting this way. So that's one aspect. Then on the methods aspect, you can look into learning more about different kinds of neural networks. So here we were just working with simple vectors or arrays of numbers as inputs. What if you have, let's say, a 2D grid of data, let's say an image. Okay, so an image is a pixel which represented as a matrix. So how do you deal with such image type data? Or if you have, let's say, time series, okay, so you have some kind of sequence where the measurement or maybe some, the data at one point is related to the data at the previous time point. And you have to make some forecasting predictions. So what are the machine learning models or methods for data structures that are not vectors. So these are sort of the two ways I would recommend. Exploring data, understanding what is the type of data you're dealing with. Second would be dealing with the method side. Yeah. And lastly, I do have a very simple feedback form. I would really appreciate if you could all please fill it in. Shouldn't take more than a couple minutes. I just put it in the chat and would really appreciate any feedback of how we can improve this going further. Okay, and yeah.
Thank you so much, Sid, and also thanks to your assistants. It's been a pleasure, and thank you so much for the presentation, the exercises, the demo. It's been really inspiring for everybody. I will encourage everybody to check the Material Pioneers website, where we will store all our workshops and some more informative documents about these workshop sessions. If you have suggestions, ideas, whatever you would like to see around coming from Material Pioneers, 4TU Data, and Open Science Community Delft, we will be really happy to hear from you and to just learn more about how to help you out. And yeah, I guess that's it. Thank you so much. Thanks, everybody. And feel free to reach out to us at info@materialpioneers.com to ask questions and give us suggestions.
Thank you, everyone. And also thanks to Prakash and Kuber for helping out with the workshops. And would really appreciate if you could fill out the feedback forms. Yeah. Cool. Thank you.
Thank
Thanks,
you.
everyone.
Bye.
Thank you. Bye.
Bye.
Thank you, Sid.